Recording. Don't worry, your faces aren't here. Okay, so we were talking about just the structure of the periodic table, and so like the names of the groups and whatnot, okay? My screen is like tweaking out. Please just move this window away from the shared application. All right, not my problem. All right, so hopefully you can't see that. Everybody, this group right here that I'm circling in black, notice I've left hydrogen. Oh my God, that's a really bad rectangle. Okay, this group right here are called the, that's right everybody, good job, the alkali metals. So if you just want to kind of like sketch yourself a rectangle or whatever, group number 1, alkali metals. This group right next door to them, the entire group next to the alkali metals are the alkaline earth metals. Okay. Luckily, we do not have to learn names for the next couple of groups, okay? We do not need to know the names for the boron family, the carbon family, the nitrogen family, and the oxygen family, because those are just the names of the elements at the top of that list. And then this family right here, group number 7, those guys are called the halogens. And group number 8, helium all the way down, these are the noble gases. And hopefully you guys remember that those are called the noble gases because they are non-reactive. With their 8 valence electrons, they don't need to lose electrons to become stable. They don't need to gain electrons to become stable. This group here in the middle, this D block group, are called the transition metals. And then the very last block down at the bottom, these guys down here, these are called your inner transition metals. Oh my gosh, I forgot this periodic table actually had those group names on it. They already color coded it for us, and here I am writing in like really ugly handwriting. Okay, so red are your alkali metals, those orange ones are your alkaline earth metals, yellow transition, then the halogens here in like this purpley blue color, and the noble gases in purple. Okay, so those are the names of the groups. I also want you guys to know the types of the elements on the periodic table, okay? And there's 3 different types of elements, and the types of elements, honestly, you guys, is much even more important than the type of elements is even more important than the names of these groups, okay? So how they behave depends upon whether or not they are metals, non-metals, or metalloids, okay? And remember, the metalloids are the ones that sort of behave like metals and like non-metals. They've got properties of both. And your metalloids are in this general area along that diagonal sort of stair step. So the elements along here are metalloids. You don't need to memorize which ones they are. Just know, generally speaking, that everything to the left-hand side of that squiggly line, all of these elements over here are metals. Metals, all of them. These guys are metals, these guys are metals, those guys are metals. The only one who's not a metal, hydrogen. Hydrogen's a non-metal, okay? And hydrogen is like these other non-metals that all exist up here on this side of the periodic table. And just think about what you know about metals, right? Metals are shiny, they are conductive, they're malleable, you can bend them. And non-metals are the opposite, right? Non-metals are brittle, they are dull, most of them are gases, some of them are solids, they're non-conductive, so they're just like, basically they have the complete opposite properties of metals. And then the metalloids have properties of both. That was that silicon chip that we used in the density experiment, and I smashed it. When I smashed it with a hammer, it shattered into 1,000,000 pieces, but it was really shiny like a metal and it conducted like a metal. So that one was kind of had weird properties of both. Okay, so that's the structure of the periodic table. I want you guys to remember that it's organized by increasing atomic number, which is your number of protons. okay? So like number 1 is number 1 because hydrogen has 1 proton, and number 2 is number 2 because it has 2 protons. So it's by increasing atomic number. But the super cool thing about the periodic table is that when you organize it that way, every 8 elements, you get a periodic repetition of properties. So like lithium and sodium and potassium, those metals that I showed you in that demo, they are all similar. They all react with water. They all have 1 valence electron. So while the periodic table is organized according to increasing number of protons, it also tells us a lot about electrons. For example, everybody in group number 1 has how many valence electrons? 1 valence electron. Very good. Talking into the abyss. Okay. Everybody in group 2 has 2 valence electrons. This is group 3, 3 valence electrons. 4, 5, 6, 7, 8. Okay. So when we move on here to talk about electrons, if you're confused, the only thing you absolutely need to know is that those group numbers at the top tell you how many valence electrons a substance has. That's the most important. And let's just remind ourselves that valence electrons are the outermost electrons. They are farthest from the nucleus. And we care about them because they determine behavior. And bonding. Like how the element bonds with other elements to make compounds. Okay, now I've started talking about electrons. And so you're like, okay, well, back in middle school, we learned that the electrons are in these, rings around the nucleus. And that was the Bohr model of the atom. Okay, that was the model of the atom that you guys learned in 8th grade, was the Bohr model. And that model is not bad, right? Like there's a lot of really good things about that model of the atom. Okay, so if you still think that the atom looks like this, like here's your nucleus with protons and neutrons, and you're like, all right, well, the electrons are outside the nucleus. That's true, they are outside the nucleus. Bohr didn't know all the details. Oh my God, I don't understand why my handwriting is so bad today, you guys. That is the worst looking Bohr model I've ever seen in my entire life. Okay, so Bohr said that the electrons were in these energy levels, like energy level number 1 and energy level number 2 and energy level number 3. And like, yeah, it's true that the electrons are in these energy levels, but it turns out that they're not these set circular rings, okay? Before we talk about like where the electrons actually are, there's one more thing I want to use the Bohr model for, and that's to remind you guys that these electrons can move between those energy levels. So hopefully some of you guys did that little at-home lab experiment last week where you took a Q-tip with some salt on it and you stuck it in your stove, or the stove top, your stove. I'm confusing stove and oven. You take your Q-tip and you stick it with the salt in the flame of your gas stove, and you saw yellow light. And the reason why you saw yellow light is because the electrons move up in energy level. They get excited when they get heated. And then when they fall back down, they have to emit the amount of energy that they absorbed. They have to emit that as a photon of light. And with sodium, you saw yellow light. But if you were doing like potassium, you would have seen, that's orange, I wanted purple. With potassium, you would have seen purple light. Like when I put the piece of potassium metal into the water the other day, the flame burned purple. Okay, so like you get different colors of light from different elements. And this is how like fireworks work and stuff. And it all has to do with electrons transitioning between energy levels. And there's a bunch of different colors of light that you could possibly see. Like in our visible spectrum, there are a bunch of different colors: red, orange, yellow, green, blue, indigo, and violet. These are the different colors of light that our human eyes can see. And the red light is the lowest energy light that we can see, and the violet light is the highest energy light that we can see. And we skipped all the calculations involved with this, you guys, but we can actually calculate how much energy these electrons have and how much energy they're emitting when they're jumping around the atom. Okay, now, this model of the atom is all right. Like, it's good in the sense that electrons have energy and they're outside the nucleus. But it turns out that they're not in these set circular orbits. And this is where, if you weren't here, this is going to seem bonkers, but don't worry about it, okay? We learned something called the quantum mechanical model of the atom. Quantum mechanical model. Oops, sorry, I forgot to turn off my phone. Aren't you guys so glad that you can be on your phones during class now? Oh, it's Miss Bowker. Okay. This quantum mechanical model is different from the Bohr model because the Bohr model said that the electrons were in set circular orbits, okay? The quantum mechanical model of the atom recognizes that we don't actually know for sure where the electrons are. Instead, we say that the electrons are not in orbits, but they're in these things called orbitals. They're not so different, you guys. Orbitals are areas of probability where we think the electrons exist. Okay, so it's not based on certainty, it's based on probability. And these areas of probability are three-dimensional. They're not like these two-dimensional orbits, okay? They've got certain shapes. They've got crazy shapes. And just like the Bohr model, though, they also have certain sizes, like they get small to big around the nucleus. And they can each hold 2 electrons in them. And this next thing that I'm about to draw is like totally wackadoo, and we never draw it this way. But when I say these three-dimensional things with crazy shapes, you're like, what are you talking about, Ms. Rivera? I'll show you. Imagine these 3 axes coming together. At the center is your nucleus. Okay, so I'm trying to show 3 dimensions here. Here's what the orbitals look like. The first one is a sphere around the nucleus. The second one is a bigger sphere around the nucleus. The next one is like a dumbbell, or I don't know what you want to call that shape, around the nucleus, like this where I'm coloring in here. That's the next one. And then the next one is lying along a different axis. If you did not learn this, don't worry about it. If you did learn it, you would know that these are called P-shaped orbitals, okay? And then the next one is another big, huge 3s orbital. And then the next one is the 3p. I could keep going and going, you guys, but like this is gonna get totally bonkers. This is not a useful diagram for us, okay? So instead of drawing it like this every single time, we wrote things called electron configurations. And there's 3 different types of electron configurations that we can write. So the 3 different types of electron configurations, remember, these are just like, this is like an address that says where all of the electrons in the atom are. Okay, so instead of like this nice easy Bohr model where I just say, oh, the electrons in the N2 or the electrons in the N3, now my address is getting a lot more complicated, okay? Because we have to address the shapes and the sizes of these areas. So we don't have to memorize this. We can use our periodic table to help us. So I'm going to scroll back over to a nice clean periodic table. In order to write an electron configuration, all you need to know is that this area on the periodic table, these elements are in what we call the S block. So is helium. Okay. This rectangle down below helium, this is my P block. The transition metals here in the middle, all of these guys here in yellow, this is my D block, and the energy level goes down by 1. Again, please don't quit on chemistry. If you weren't here for this, it's okay, you don't need it. And this block down here is called your F block. We're not gonna do the F block though, so don't worry about it. It goes N-2. Okay? So, for those of you that were here, let's review. This is your first energy level, your second, right? The periods are your energy levels. Second energy level, third energy level, fourth energy level, fifth, sixth, seventh. All right, this has been a lot to write down. I don't know if you're writing or not, but don't worry about it. Here's what you should write down. Let's do an electron configuration for selenium. Or maybe I feel like we already did selenium as an example. Let's do, should we pick a really big one? One that's really annoying and far away. Let's do antimony, SB. Okay, so this element, I shouldn't have used green, here on the periodic table. All right, we want to write down where all 51 electrons are. That's a lot of electrons, okay? So let's do it. We can do it, I'm confident. So the electron configuration always starts with up here in the first period, the 1s orbital. And I can fit, remember, 2 electrons in there. So the first part of my electron configuration is gonna be 1s2, because I'm gonna put 1, you just count the elements, 2 electrons in the 1s. So we're gonna go 1s2. And then the next one, second energy level, still in the S block. So 2s1, 2s2. That one's gonna be full as well. 2s2. You guys are gonna get dizzy with all this back and forth. Keep reading across. That's 2s2. Keep going across. Now you're in the 2p. 1, 2, 3, 4, 5, 6. 2p6 comes next. Okay. And then what comes after the 2p comes the third energy level, 3s. And after that, keep going across, is going to be the 3p. 1, 2, 3, 4, 5, 6. 3p6. So what did I say? 3s2, 3p6. All right. What comes after 3p6? All the way across, 3p6, that's argon. Keep going. Now I'm in the 4s2. That's here and here. 4s2. Then what comes next is the D block, but the energy level goes down by 1. So yes, we're in the fourth period, but this is going to be the 3D. Okay, so it's going to be 4s2, 3D, 4s2, 3D, and that's going to be full, 10. We're going to count 10 electrons across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, back in the P block, the energy level is 4 again. So 4P, 1, 2, 3, 4, 5, 6. 4P6. Almost there. Keep reading until we get to that element. Now we're in the fifth energy level. So this is going to be 5s2, 1, 2 electrons. And then 4D all the way across, 4D10. 5s2, 4d10. And then keep going. Now we're in the 4p, 1, 2, 3. I mean 5p, sorry. 5p3. You guys can always type a question or interrupt me if you have a question. It's awfully quiet out there. Okay. This big long thing that I just wrote is called the longhand, which is good news, right? That it's the longhand because that means there's a shorthand. And the way that we write the shorthand is, for those of you that have been doing this, you see that this pattern just repeats itself over and over and over and over again. So if we were to look at the noble gas that comes before antimony, so I go up and over, that's krypton. If I put krypton in brackets, that takes care of the whole electron configuration all the way up to the 4p6. So all I do is I put the noble gas that comes before it in brackets. So I'm going to put krypton in brackets. And by doing so, I don't have to write any of all of this, which saves me a lot of time. All I have to do is write what comes after it. 4D10, 5P3. And there's one other thing that we can do with this, and that's to draw what we call an orbital diagram. So instead of drawing, okay, so this right here is the shorthand, also called the noble gas notation. Instead of drawing all of this big, huge mess that I just drew, instead we can draw just little lines or boxes to put the electrons in. So for the 5s, I just draw one line to hold, because remember, every orbital can hold 2 electrons. For the 4D, I need to draw 5 lines, because there's 5 different d orbitals, each that can hold 2 electrons, right? So 5 times 2 gives me the 10. And, oops, someone's coming in now. And then I'm going to draw 3 lines, 1, 2, 3, for my 5p. Bye, Matisse. Okay, so now I'm going to put my electrons in there, you guys. So I need to show 2 electrons in the 5s, 1, 2. I need to show 10 electrons in my D, 1, 2, 3, 4, 5. Remember, spread them out first. 6, 7, 8, 9, 10. And I need to show 3 electrons in my 5p. Spread them out. 1, 2, 3. This right here is called the orbital diagram. Normally we would do it for the whole entire thing, but I just did it for the shorthand. Okay, so if you tuned out because you were like, yeah, I didn't learn any of that, tune back in, because now is here where you can understand stuff, and it's going to be very important. We care about these electron configurations because they show us the valence electrons. The valence electrons are the electrons in the outermost energy level. So if I'm looking at the outermost energy level, what's the biggest number I have here? Biggest number I have is 5, the 5s and the 5p. That's my outermost energy level. How many electrons are in those orbitals? 1, 2, 3, 4, 5, right? Or I could just look up here. The 5s has 2 electrons in it, and the 5p has 3 electrons in it. So this element has 5 valence electrons. And this is the important part, okay? You could have gotten that just by looking at the group number. If antimony is in group number 5, right? Because if I number all of these groups again, like we did on the periodic table up top, this is group 1, group 2, 3, 4, 5, 6, 7, 8. Antimony's in group 5, so it has 5 valence electrons. And you're like, oh, Ms. Rivera, then why do we learn all that nonsense? Because it's actually important for other things. So in AP, we're going to learn about some properties that elements are going to have based on their electron configurations, based on the fact that these are unpaired electrons. All this fancy stuff is very useful as we learn more and more chemistry. But for you guys, all you need to know is number of valence electrons. And the other thing you need to know about valence electrons is how to draw them on an element symbol. These are called Lewis dot diagrams. So you write the element symbol. We were talking about antimony, which is Sb. And I want to put 5 valence electrons on it. We just go in order clockwise. 1, 2, we don't pair them up till we have to. 3, 4, 5. These are super important moving forward, okay? So like, know how to do this and know how to do that. Any questions on those 2 things? Okay, we're almost done with our review. Last little bit is talking about what we talked about yesterday, which are just the trends on the periodic table. And I'm not going to go into the long-winded explanations as to why these are the trends. We talked about that yesterday. I'm just going to remind you of what those trends are. And I think I have one last periodic table to draw on down here. Aha, yes, I do. Okay. I always just like to give myself a visual, even though I'm a crappy drawer. I think the visuals are helpful. Okay, so, no thing, go away. I want the black pen. And I want this keyboard thing to go away. Go away. Okay, so my black pen. First trend I want to show you guys is radius. When you go down a group on the periodic table, oh my God, I don't know why I can't draw a straight line today. When you go down a group, radius gets bigger because we get bigger and bigger energy levels. Okay, so radius increases going down a group. Radius increases. And having just talked about electron configurations, the 1s, the 2s, the 3s, the 4s, the 5s, and so on, it should make sense that that radius is getting bigger. And when we go across the periodic table, radius gets progressively smaller. Okay, so when we go this way, radius decreases. Because when you go across a period, you get more and more protons in the same energy level. And so those protons pull the electrons in tighter. And so when the electrons come in tighter, the atom is now smaller. The other thing that I want you guys to know about radius is that when atoms gain and lose electrons, their radius changes, okay? And this is also super important for our next unit. If I'm talking about, let's say I'm talking about lithium. Lithium has the electron configuration 1s2, 2s1. And if you don't know that, don't worry about it. You know that lithium has 1 valence electron. And you're like, okay, it's got 1 valence electron. There it is. Atoms will gain or lose electrons in order to get stable, to get to a full valence shell. So lithium has a choice. Lithium could lose this 1 valence electron, right? This 1 valence electron could go flying off, bye-bye electron. And this whole energy level now goes away and is empty. And now the 1s is a full valence shell. That's in fact what happens. Lithium becomes a 1+ ion by losing that valence electron. And it becomes smaller. So the radius decreases because it lost that whole valence shell. The other thing that lithium could have done is it could have gained 7 electrons to get to a magic number of 8, but losing 1 is much easier than gaining 7. So losing 1 is what happens to lithium. And so when lithium becomes lithium 1+, we now call it a cat ion. This is what we call our positively charged ions. The T looks like a plus sign. That's how you remember it. And cations are smaller than the original atom that they come from because they lose that energy level. And then the other thing that can happen is, like, let's say instead of talking about lithium, a metal, what if we were talking perhaps about, let's say, like sulfur, a nonmetal. Sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. And you're like, oh, I don't like that, Ms. Rivera. Okay, don't worry about it. Sulfur has 6 valence electrons. Just draw it. 1, 2, 3, 4, 5, 6. For sulfur to get happy, it needs 8 valence electrons. So it could either lose all 6 of these, like it could lose all of those in the 3s, and then it would have that full second shell. Or it's probably easy for it to just gain an electron there and gain an electron there, right? Gaining 2 is easier than losing 6. This is going to give sulfur a charge. It's going to make sulfur a 2-. And when that happens, those extra 2 electrons went in there. So that now sulfur's configuration ends with 3s2, 3p6. Now it's got its 8 valence electrons and it's happy. It also has a 2- charge because it gained those extra electrons. When this happens, we call it an anion. The an prefix meaning negative. So it's a negative ion. And it's going to be slightly larger. And you might not think that it's going to be larger because see how it's still in the 3rd energy level as it was before? It's because these extra electrons create repulsion. And so the p orbital is going to get a little bigger. Okay, so these ionic charges, these Lewis dot structures are the most important things. We also talked about 2 other trends, but they're not super important in terms of being able to move forward. We will use them a little bit later on. And those are called ionization energy and electronegativity. When we go down a group and the electrons get really far away from the nucleus, they become a lot easier to remove. And so when we go down a group, they require lower ionization energies. So maybe I shouldn't say like that. Maybe I should say ionization energy decreases because the electrons are really far away. So they're much easier to pluck off than on these small atoms. So when we go across the periodic table and the atoms get smaller, ionization energy increases. And then the last trend we talked about was like love for electrons or electronegativity. It has the same trend as ionization energy. So like you could just say ionization energy and electronegativity decrease going down. Ionization energy and electronegativity increases going across. It's just love for electrons in a bond, you guys. So if francium has its electrons super far away from its nucleus, it barely loves its own electrons. It's definitely not going to be able to pull on another atom's electrons in a bond. Okay, so that's why when you go down a group, there's really low electronegativity values. And when you go across a period, there's really high electronegativity values because the atoms get really small. And so you might think that helium has the highest electronegativity value because it's the smallest atom. But it doesn't, because definition of electronegativity is love for electrons in a bond. And the noble gases don't bond. So fluorine actually has the highest electronegativity value, even though helium is the smallest atom. Helium is the smallest atom. Francium is the biggest atom, but fluorine is the one that's got the most love for electrons. And that'll be important later when we figure out polarity. Like in bio, when you talked about polar and non-polar molecules, that's all gonna have to do with electronegativity and love for electrons. Okay, so again, the most important things for you guys to be able to do and know in order to really understand chemistry is group numbers, right? So 1 through 8, Metals versus nonmetals, very, very important. Valence electrons, being able to identify them, very, very important. Even if you're just identifying them based on group number, okay? So if you just look at the group number and you get your valence electrons, awesome. And being able to draw a Lewis dot diagram. Those are the things that you absolutely need to be able to do. If you have any questions on that stuff, I'm gonna stop recording or pause recording. Okay, so this is additional information for honors now. We learned about something called quantum numbers. And what quantum numbers allow us to do is to identify singular electrons in a sequence. Okay, so for example, you know, it's nice to know where all of the electrons are, and it's nice to know how many valence electrons there are, but there are times when we're doing things like quantum computing and building MRI machines and like really getting into the nitty-gritties of how electrons behave, where we need to know everything that there is to know about one individual electron. Oh, am I sharing my screen still?
Yes.
Okay, thank you. All right, so I just circled an electron in purple. And let's say that you guys want to know everything there is to know about that one valence electron. You would need to know first the energy level that it's in. That's principal quantum number n. And the principal quantum number n corresponds to the size of the orbital, the principal energy level. It's in the 5th energy level. So my n is 5. The next thing I would like to know about that electron is which of those p orbitals is it in? Because you guys remember, p orbitals can lie along any of these 3 axes. It could lie along the x-axis, could lie along the y-axis, or it could lie along the z-axis. That's what these 3 lines are representing. Oh, I'm getting ahead of myself. You guys, please excuse me. I just tried to jump to the m sub l. The next thing that I want to know about the electron is the shape. Okay, ignore what I just said. The shape of the orbital, like, is it in a spherical shaped orbital? Or is it in one of these dumbbell shaped orbitals? Or is it in a D shaped orbital? It's in a P shaped orbital. So like, that's the next thing I want to know. And unfortunately, P is a letter and not a number. So do you guys remember S, P, D, F? We just tag them as L equal to 0, 1, 2, 3. So because this is in a P-shaped orbital, I'm going to give it an L of 1. Okay, now is the time where we need to address whether or not it's in the X, the Y, or the Z axis. Okay, is it in this orbital, or this orbital? And the way we do that is we just number line it. So we go -1, 0, +1. And if we were number lining the D, it would be like 0, +1, +2, -1, -2. And for the S, it would just be 0. Okay, so that was the M sub L that I tried to talk about before I talked about L. My M sub L would be -1. And then the last quantum number refers to the spin of the electron, M sub S. Because potentially there could be a downspin electron in here. There isn't, but there could be. So my final quantum number is a +1/2. If it was a downspin electron, it would be a -1/2. So being able to assign quantum numbers allows us to tag individual electrons in the sequence. And then next year in AP Chem, we'll talk about the fact that because all 3 of these electrons are unpaired, we're going to have certain magnetic properties of the element. So certain elements are magnetic and some are not. That has to do with how many paired and unpaired electrons they have. We're also going to use these complex orbital diagrams in order to explain bonding between atoms, which gets really kind of cool and fun. Okay, so for honors, if you're thinking about AP next year and you sort of missed out on this electron configuration stuff, go back and watch those lectures that I posted. And listen, AP is going to be a little funky next year. We're going to have to just get everybody kind of on the same page at the start. So don't worry about it too much. All right, was there any like additional honors type stuff I want to talk about? Oh yeah. We didn't do the math involved with these, you guys, but like when I was talking here about how much energy this light has, like the amount of light that gets emitted, or sorry, the wavelength of light that gets emitted, we can actually measure how much energy this light has with an equation. And we didn't do any practice with this equation, but here it is. Energy is equal to a constant times the frequency of the light, okay? And again, you don't need to know these constants or anything like that, but it's just kind of like a little heads up for next year, that we can in fact measure the amount of energy that light has. Okay, so E is for energy, H is Planck's constant, and this little guy here is for frequency. So these might be familiar to you from physics. E is energy, it's measured in joules. This is frequency, and it's repetitions of the wave per second, which is 1/seconds, or hertz. Again, we didn't really talk in detail a lot about this because that's right when we sort of moved to this online school nightmare. So when we're talking about waves, you guys, if this is a little review for physics, wavelength is the distance from here to here. This is like the wavelength or the peak to peak distance of your waves. Ugly wave. That's your wavelength, which is lambda. And however many times this wave repeats per second is the frequency. So if I had a wave with a much shorter wavelength like this wave has a much higher frequency. Because over that same period of time, this wave repeated itself like 4 times, and this wave only repeated itself once. So this example of the wave has a long wavelength. This one has a short wavelength. This one has a low frequency. This wave has a high frequency. And so the relationship between wavelength and frequency is C equals lambda nu. Like you guys can see that like when the wavelength goes up, the frequency is going to go down. Or when the frequency goes down, the wavelength is going to go up. They're inversely proportional. And what connects them is the speed of light, because all electromagnetic radiation moves at the speed of light. I see that somebody has a question, so hang on one second. Let me just, this is wavelength, typically measured in nanometers. All right. What is H? H is Planck's constant. Like you want to know the actual value for it? It's a gross number. You're gonna be sorry you asked. 6.626 times 10 to the negative 34 joules times seconds. And the speed of light is 3 times 10 to the 8th meters per second. So in order to use these equations, you just have to make sure that everybody's in the same unit, right? Like if you're measuring a wavelength in nanometers, but the speed of light is in meters per second, we would have to convert our nanometers to meters. I'm not going to ask you guys to do any calculations with these equations. I'm just sort of making sure that I at least hint at all of the, or introduce you to some of the vocabulary and equations that you guys are going to see next year in AP, even though we're doing sort of like this abbreviated honors course. Okay. So next year we'll do calculations with these, but it's super easy. It's just plugging and chugging. You guys can solve 3 variable equations, or at least you better be able to. Okay. So, yeah, that's it, I think. Oh, I know we talked additionally yesterday, but since we just talked about it yesterday, I don't know if you guys need to like actually review it. But when we were talking about ionization energy, we were talking about the fact that you can actually measure successive ionization energies. Like if you had something with more than 1 valence electron, you would have to take off, take off the first electron, then take off the second electron. And those ionization energies are successive, right? So like if I had, let's say, magnesium with 2 valence electrons, the energy needed to remove this first electron would be ionization energy number 1. And the energy needed to remove this second electron would be ionization energy number 2. And these things keep getting progressively bigger in magnitude. Like it takes more and more energy to remove electrons as this thing becomes positively charged. And if you try to remove a core electron or a non-valence electron, like if I looked at what ionization energy number 3 would be for magnesium, would be huge. because it only wants to lose 2 valence electrons. Would be huge. Can you guys tell that this online teaching is starting to get to me? I don't like it. Okay, tell Mrs. Rivera to suck it up. I should have stopped recording